we'll get into the dynamic analysis and runtime debugging lecture. So I always like to kind of preface this with kind of my own opinions about the limitations of static analysis. I also like to kind of describe static analysis as the kind of looks like analysis, right? So I'm looking at a piece of malware or a malicious document or something like that. I'm trying to explain what it looks like, and specifically I'm trying to explain what the bad parts of it look like. The goal being that if I find if I do it well enough, then my description will positively identify other things that may be the same or derived tools that may have slightly different content in them. So that's kind of in contrast to the behavioral side or the dynamic side, which is what I like to call the behaves like or acts like analysis. In this case, I've got I'm going to start talking about the network and similar like behavioral detection techniques, things like that. We'll start looking at the basically the activity and the work and the effects that happen outside of the actual file itself. So, one thing I'll say, the reason why we do this is because many times you can look at a file, you can analyze it, you can maybe describe what it looks like it does, but you don't actually know all the time if it actually performs those actions, if it actually does those effects, until you actually try running it and try poking at it. Similar to, say, a common shorthand for this type of analysis is called detonating, and the reason they say that is it's similar to, it kind of comes from the whole like weapons analogy, where if you think about, say, the bomb squad or something like that for the police, if they happen to have a threat that's alerted to them, they may go in there, recover whatever the device is, that type of thing. They don't often entirely know how the thing's going to behave or how it's going to act or whatever. So they do controlled detonation or controlled activation to try and see what happens. And then after that, they inspect everything that occurred, the effects that happened within their contained environment. So that's basically what we're doing here. And then from that, they figure out how to identify what was used to build it, what would happen if it happened to explode in a unsafe environment, say in this case the malware running on a system that has sensitive documents on it or something like that. So runtime analysis, or as I mentioned at the beginning of my previous slide, it's the kind of behaves like or acts like analysis. So basically you want to open, and this is probably very straightforward or very obvious, basically opening or kicking off the attack inside of controlled environment. So this is one of the reasons why I had you do that attack that we played with during the second week of class or so, and basically to see this occur. So two common approaches to this. I'll say the most common one that you'll see nowadays is using a virtual machine hypervisor or some sort of emulator or simulator. That's the approach we'll use in class, right? So we'll be using VirtualBox, which I have like the link for the fifth or sixth time right here. So we'll probably end up using VirtualBox, or some of you may use VMware. It is not uncommon for people to use what's called a bare metal hardware malware lab. That's literally like physical computers, sometimes connected to a what's called an air-gapped network, or basically a network that doesn't have any connection outside of the handful of systems. So that's not uncommon. It is much more expensive, and thus we're not going to mess with it here. But those of you who might end up going into the job market or something like that, to companies that do malware research or organizations that do it, you might actually get to play with this type of malware lab. So,
requires internet access?
So we'll get to that. Question was, what if the malware requires internet access? So I will say a lot of malware requires internet access in order to operate, or not necessarily in order to operate, but in order to perform all functions, right? So there actually exists some simulators that you can run on other computers or in other VMs, and then you can route the traffic from one VM to the other. So you basically trick the malware into thinking maybe it's connected to the internet by actually having it talk to a fake web server or something like that. And then maybe you can actually collect some of the results, like some of the resulting functions down the line, and we'll actually demonstrate that in kind of later lectures. So, but yeah, that's a really good question. That's actually a problem that happens a lot, or something that we have to contend with a lot. So I usually like to think of kind of runtime analysis as what I like to call trying to analyze what's called the runtime attack surface. So the attack surface being the environment in which the malware can work and run and everything like that. So in this case, that ends up being maybe a computer Windows system, or maybe a set of Windows systems. So I often like to carve up the attack surface into these 6 bins. So file system changes. So as you're all aware, you have a file system on your computer, files, directories to work with, organize information. Malware knows this. Malware is going to try and achieve its objectives going through that. Execution environment, so separate from just the file system, because all those programs on your computer themselves don't really do anything, just sitting on the hard drive. They actually get loaded up into CPU, actually into RAM and the CPU to execute the instructions. So I generally consider that to be a separate execution environment, or a separate part of the attack surface, basically a separate domain to analyze. The operating system and user configuration, so this is the configuration information that's in both I should say the administrator level stuff. So for instance, what services are running, whether to force the users to log in or auto login as a specific user when the computer boots up. Those types of things are considered operating system configurations. And then user configurations is like what image my desktop has, or what theme I'm going to use on my taskbar, or even what my default web browser is going to be, and stuff like that. All those things are considered to be like user configurations. And then persistence mechanisms. This is probably one that's really key, but also not necessarily always obvious. All systems have all of Windows systems generally have mechanisms to allow software that's installed to have components that run on boot up, or maybe on user login and stuff like that. So the goal of most of the intruders is to try and get malware that's constantly executing on a system. However, systems aren't constantly powered on and running the same session all the time. So what the actors will do is they will take advantage of a lot of these, what we call persistence mechanisms, to basically persist. So they'll take advantage of a lot of the mechanisms in Windows that allow a driver or an application or a piece of software to basically run on reboot. Basically,
the registry part of that.
What's that?
The registry, Windows registry, is that part of?
Yeah. Yep. Yeah. Windows registry is included in this. So some of you are familiar. Windows actually has multiple locations where it stores information that informs the operating system what programs to run on startup. And the Windows registry is one of those locations. So basically doing registry forensics will, basically cover like 2 of these buckets, or I should say will be a component of 2 of these buckets. So there's also system and object user resources. These are also most of the time hidden from view unless on a Windows system you've actually written a lot of applications that do a lot of intercommunication. So In our case, when we're dealing with malware, a lot of times we end up dealing with software that was written to actually interact with other programs on the computer, other legitimate programs sometimes. In order to achieve this in Windows, most of the time you need to create like system level or user level object resources. Some of these have very specific arbitrarily chosen names. Some of those arbitrarily chosen names are actually hard-coded by, say, a malware author or something like that, or need to be hard-coded by a malware author. For that reason, being able to do forensics on the system and user level objects that are collected in the Windows kernel or the Windows operating system space, being able to enumerate those things and actually forensically analyze them is also very valuable to us. However, that's typically not something that is, that is readily apparent to most of the Windows users, and even a lot of developers, unless, as I said, you deal with a lot of like inter-process communication, stuff like that.
You know how Windows has a default administrator user account?
Yeah.
Does malware take that?
Yes.
But most people don't know that.
Yeah. So yeah, Windows a lot of times has a default administrator account. Sometimes that's set up by default on a lot of systems. Other times you can create your own account, or I should say you can create your own administrator account with a different name. There's also what's called a system account that exists in Windows as well, where a lot of the drivers and system services run. So we'll also get into that stuff later, but yes, malware takes a lot of advantage of that very frequently, and there's a number of mechanisms it uses to try and break into, I should say, to try and get malware from running as a user and get it to running as the system administrator or something like that. So that would be, that could involve some of this stuff, the system and user object resources. Additionally, I would say that this space as well, where the arrow is, also covers a lot of the cases where maybe there's other tools that want to steal passwords or steal certificates and things like that. May play a piece. But as I said, it's very often malware trying to interact with other programs, or maybe malware trying to interact with other components of malware. So, and then finally, the last kind of domain that I carved this up into is network. And that's where your computer, your system ends up actually causing effects that might impact other systems in the environment. Or you basically are able to basically monitor network traffic, things like that. And we'll get into that a little bit. I would say overall, I don't necessarily consider this to be an exhaustive list, or even the same kind of binning that other people will use. It's kind of very subjective science here, so I'll let you kind of know that right out of the gate. This is just kind of how I've been carving up these things. And a lot of this is because I can pinpoint specific tools that are useful for inspecting each one of these things. So, great. So file system modifications, we'll start with that. That was the top bullet from this list. So, most of the time when they're trying to, utilize remote access, it's gonna involve making file system changes. Most systems, there's a volume directory. So in Windows, if you're using NTFS, that's very often the master file table. If you're using the FAT file system, there's actually basically a top-level directory called the file allocation table, which is how the FAT file system gets its name. It's basically a hierarchy of a series of those. So NTFS has a much more well-structured, structured file system layout, and I'm not going to get too much into the file system internals in this lecture, but And the goal here is just kind of keeping in mind that there's basically a large list of all the files and directories that exist on the system. And that can actually be inspected after an attack has been performed in a system to actually see what changes were made, and also sort them by like time and see what happened in a certain window at time. Sometimes there's also a file system journal. So some of you are familiar with journaling file systems. Keeps an index linking names of file objects to their content, stuff like that. So those are all basically like, records of file systems. So, so what I did was I put together a sequence of steps that comprises an attack, and what I'm going to do is I'm going to try and map it to each one of these domains. So in this case, excuse me, in this case, the file system impact. So if we just look at the attack and kind of ignore the parentheticals that I've got up here, basically the users, we'll say the user was given a link to a bad PDF file, right? It's hosted on the internet somewhere. So they end up clicking the link and they download the PDF into downloads folder. They open that PDF, so they double click on it, or maybe they go into their downloads menu and then they open up the file that was downloaded. PDF, it ends up causing Acrobat Reader to run. So Acrobat Reader runs because PDFs are associated with Acrobat Reader in the user configuration. Then bad PDF exploits Acrobat Reader. And so while it's loading, it causes Acrobat Reader to break. Once Acrobat Reader breaks, then attacker shellcode that was inside of the PDF writes 2 more files into the temporary folder. So into the folder that's represented by this user environment variable here. And then the shellcode opens both of those. So it tells Windows, using a specific function call, tells Windows to open good.pdf and then also to open bad.exe. The order doesn't really matter. It could open them in either order. Then bad.exe, once it's open, it actually deletes the original bad.pdf. And then bad.exe writes a symlink so a symbolic link, or some of you might know this as a Windows shortcut. So it writes that into the startup folder underneath the start menu for the current user. Then, after it's done that, it establishes a communication link. So it opens a connection to some remote IP address or some remote domain name or something like that, and establishes basically an ongoing, opens a communication channel that way. So these 8 steps. So if you think about it, this is one example. There's a lot of different varying examples, but when we're talking about dynamic analysis, being able to document the kind of sequence of steps, the movement from one to the next, with the different pieces, you can see in, I believe, almost every single case. This one basically has a link to this one, has a link to this one, which then exploits Acrobat Reader. Probably should put with some shellcode embedded in it. The shellcode then does something, then does something else. Then one of the things that happened in number 5 causes number 6 to happen, and number 7 to happen and number 8 to happen. So kind of we have this chain of events that goes like our causal link, that type of thing that goes from one to the next. So trying to explain dynamic analysis when you are analyzing how a program ran is a matter of trying to see all the activity happening on a system, which in addition to this program running or this stuff happening here, there's also a lot of stuff that Windows is doing behind the scenes. So it's being able to identify that this stuff's going on and basically what the sequence of steps is, which might require digging into a lot of different tools.
So I guess malware deletes the bad PDF to prevent analysis from detecting the root cause of the
Yep.
exploit.
Yeah, that's a really good point. So on number 6, I mentioned that it deletes the PDF that was originally downloaded in step 1. The reason it deletes that is so that if you don't learn about this, say, command and control connection until 7 days later or something, it's a lot more difficult for the incident responder to trace the chain of events back to the original email and the original download without having to dive into some really specific on system forensics. So in this case, just from the file system impact, what I ended up doing was I carved out some parentheticals that highlight the subset of these steps that actually cause some sort of action on the Windows file system. And the Windows file system has specific actions that it will log. So in addition to just telling you where all the files are, the master file table also keeps a log of multiple different types of operations. It's actually got 4 different types of operations. So it's got creation, access, expunge, and then modification, I think, is the 4 of them. So the idea being that, and if you've ever, I think I can probably go here, right? So if I go over here and look at my Windows 7 VM, there we go, properties, right? So if I look at my Windows 7 VM, you can see that I have 1, 2, at least 3 timestamps. So you can see that 1 timestamp's recorded for when the file was first created. There's a completely separate one that every time I change the file after that, it actually updates that timestamp while leaving the created time the same. And then finally, there's an access time, which means that any time I read the file with another tool, it's supposed to update the access time. And then finally, one thing that isn't always, I should say, that isn't obvious here because you have no way to retrieve it, is that there's a deletion time as well for any files where you've deleted it, which means that you didn't, and not just the moving it to the recycle bin, but actually deleting the file from the system. If you do that, then there's a 4th timestamp. And so what Windows does under the hood in the file system, and this is a really kind of important feature, is that rather than when you delete a file actually going through and writing zeros over all the sectors that the file took up and writing zeros over the old directory entry for the file, it actually just adds another directory entry to it that says that this file was deleted. And then it puts a timestamp when it was deleted. And then it marks all those fields to be available for reuse at some point in the future. So if you want to download more files to your computer after you freed up space, it will gradually overwrite that stuff. But if it doesn't have to overwrite that stuff, it also doesn't erase that stuff, which is extremely helpful for people doing an investigation on an attack like this. Because, we'll jump back to the presentation. So, bad PDF right here, I have a creation time for bad PDF in the downloads folder. Then I have an access time, which gives me some visibility as to when the user downloaded it originally, and then separately when the user actually opened it. So it could very well be that the user got this fish like 4 o'clock on a Friday or something like that, and they might have downloaded the file, but they don't feel like opening it because they want to get out and get home at 4 o'clock on a Friday. So they might have just left it in the downloads folder. And then on Monday, they come back into work, and they see that that fish is in their inbox, and they're like, okay, well, I wonder what this thing was. So at 8:30 a.m., they might open that PDF, which means that those 2 timestamps now are kind of about 3 days apart, right? That's kind of the reason why it's why it's recording these different why it's recording these different timestamps. So then the shell code, so after it opened it and ran it, the shell code actually writes 2 brand new files. So 2 new files are created with 2 new creation timestamps. The good.pdf and the bad.exe. So you got 2 new files created. You might actually get, it might actually be useful to see, say, how long it took from opening that PDF to actually creating the files. That might give you some insight. I'd say from a from like a system analysis standpoint, if if you wanted to, say, see all PDFs that were open in your environment, and then have a tool that would try and see if other files were created within such and such amount of time, being able to do this experiment, if you did get a copy of this malware, would give you an idea of what that time window would be that you would look for stuff in your environment. So in this case, it's another real handy thing to be able to collect the creation time for these After Effects. The shellcode also opens both of them, so it updates the access time. And that's probably very close, likely very close in proximity to when these 2 were written. And then it deletes the bad PDF. And so it expunges it or deletes it. I think expunge is a common term used, and that's just because the letter E is often used for this timestamp. So bad.exe deletes bad.pdf, so it actually creates that new timestamp there, and then bad.pdf doesn't show up at all in the, doesn't show up at all in the in the desktop or in the Windows Explorer or what have you. Oops. So the nice thing is that if 7 days later the user hasn't, 7 days later you detect that this network traffic is occurring and you go and forensically analyze the user's computer, maybe the user hasn't been downloading a lot of files since then. So you might luck out and still have the expunged or the deleted entry on the system that also still has the original creation and access time. And then the original creation time can give you a nice area of time to look at if you're, say, trying to look at all of the emails that the user received. So rather than going for all the emails the user received over the past 7 days, which can be a very huge undertaking, you can actually narrow the exploration down to this one small time window that is indicated by the creation time of bad PDF, or maybe indicated by both of these, right? Because you don't entirely know. Or at the very least, this one gives you a lower bound on when that email could have been received. So, but then finally, it writes this symlink in a startup folder, and then it may establish a communication link. Or it might do those in reverse order for some reason. For instance, it might establish the communication link, but then not actually create the symlink in the startup folder until much later, possibly until after an actor actually decides to start typing commands into their shell, like we did in Meterpreter, and decides that, hey, this is a very useful system. I think I will tell the malware to actually start on reboot, so that it constantly keeps connecting back. So you can also use these effect timestamps, especially when you get to the point of in this case, the bad.exe running, right? When you get to the point of the bad.exe running, you can actually use the timestamps to figure out whether the actions were built-ins in the malware or whether the actions were specific choices that whoever had unauthorized access to the computer through the malware actually had to, selectively perform. And that can give you some insight as to what the purpose is, what they were trying to do on the system. So the next piece that I'll get into, so remember we're kind of going through this list. So the next piece that I'll get into is a broad term I call execution environment. So when most of the time when you're doing, virtual machine, at its core, the virtual CPU and the virtual memory that you're using with it is basically virtualizing the execution environment. So if you've ever dealt with a cloud computing class or something like that, that whole infrastructure domain that is the virtual CPU, virtual memory, that is all the execution environment. So, so let's see. So the reason I like to select this as its own specific thing is because when you're running malware inside of a debugger, if any of you have used like Visual Studio's debugger and that type of stuff, the debugger is used almost exclusively for analyzing this stuff, for analyzing the execution environment. So the debugger is used for being able to identify what the contents of memory are for that process at runtime, what the CPU instructions are being executed, what the CPU state is, like all the registers and the flags and everything like that. All of those things are the execution environment. So the earlier discussions, I think I did, in fact, I think it was like the last class, toward the end, we did talk about a handful of like obfuscation techniques or packing techniques, things like that. So, there's a number of different packing techniques like compression and what I like to call spaghetti code, or basically having more branching instructions than you really need in order to get the job done in a particular program. So a lot of times when these are applied, the only way to analyze the actual code that the malware author wrote is by using a debugger, by actually freezing the program and being able to debug it. And that's why the execution environment I consider to be kind of a special section of the kind of analysis space. So I think the situation I explain up here is that if you think about it, when you have compressed code or something like that, if you have compressed binary code, you can't really feed the compressed instructions to the processor. You actually need a decryption routine or a decompression routine, or both of those things. And then what happens is the program feeds sections of itself into those routines, and then it puts the output of those in memory somewhere. And almost all of the compression and non-control flow obfuscation methods that exist, so compression, encryption, things like that, almost all of them work by taking a compressed block or taking an encoded block of code, basically a block of code that can't be executed natively by the processor, running most of or the entire block of code through a decoding routine, and then filling an empty block of memory with the decrypted or decoded program itself, which means that in order for the program to operate, there is a point in time when, if you freeze the program, memory has either the entire program decoded or at least a large portion of it. And the reason you have that is just because if you take into consideration all the author-written code plus all the library code and things like that, you end up having a lot of, say, function calls and if statements and switch statements and those type of things, which require your program to jump around a lot. So it doesn't just suffice to decrypt a small window of code and then delete the parts that happened before it, because most programs actually jump around a lot. You actually need to have a large section of code that comprises all the functions you're going to use and all the variables you're going to use and all the tests you're going to use contiguous in memory. Did you have a question?
Running the debugger on in this case, you mean running the debugger on the assembly code?
Yeah.
So after running the assembly
Mm-hmm.
on the EXE.
Well, so how it'll typically end up working is that you will load the EXE up in the in a debugger. So in a visual debugger, like I can just kind of give an example. Let's see. We'll just go with and then yeah. I'll just pull up this one, right? Whoops. I think I don't want to do that. Okay. I think I can go here, maybe look at it, right? Yeah. So I can go and I can say open view image, right? This is actually a really good example, so I'm glad I found this particular one. So what ends up happening is you load the program up in Immunity Debugger, and then Immunity Debugger is gonna, let me see if I can do this. So Immunity Debugger is actually gonna look at the bytes. So that's what's in this second column right here where the arrow is. So Immunity Debugger is actually gonna look in memory at the bytes. And it can start with the location, which is over here. Let's see, right? So this highlighted thing right here is actually where the program is executing. So it can go there, it can find the program because it knows where the program was executing. And then it will actually translate kind of in line the bytes into disassembly for you. So that's what's going on here. So I didn't, or I should say the person who ran it didn't have to go and run it through any sort of translator. We didn't have to generate any disassembly before we could use the debugger. So we can actually trace the code with the debugger. The other nice thing about this, and this is information that you do not have most of the time when the program is written on disk. And that is, go down here, and there's this function call right here that's happening. So a lot of times, this right here where I have the arrow is actually a numeric address, right? But what they were able to do at runtime is identify what function name is actually at that address, which isn't always something that's available at compile time or on the file on disk, but it is something that has to be available at runtime, or else this function call is going to fail. So if it can't connect, you know, if the information does not exist in the system to connect your function name to the numeric address, then this function call will fail, and the author doesn't want that. In addition, for a number of these things, you're also able to identify what the arguments are that are being passed to the function calls too, which is something else. You know what registers are being used to pass the values, but you don't know what the values themselves are because they haven't been constructed yet. So in this case, I think this one is saying EAX contains, so the EAX register contains the 32-bit value that is being passed to the H thread argument of this function call, I guess. So that's one of the other benefits that you get to have with this. And that's where it becomes really helpful because you can understand what decisions are being made. So just the other thing too that you get to do is, and we'll pick where the arrow is right here. That's a test. So as you're aware, like a lot of the branching instructions that exist, the conditional ones, typically they involve a test or a challenge followed by a branch if true or a branch if false. So in this case, this one, the test, AL, AL is basically testing the value of AL. And then if the result of that's non-zero, so if AL is non-zero, then it will jump to this address that happens to be inside of this program. The nice thing that you get to do as well in this is that if I wanted to, when the program was running, I could actually, before I get to that line, I can actually modify the code in memory. So if I realize that the program, maybe this is supposed to test the result of AL, supposed to test the value of AL, I can actually change the logic here so it'll do the inverse. So for instance, if testing that, I think the comment was brought up before of what happens if malware is VM aware, right? What do I do in that case? So if I load up the malware and then I cause it to step one instruction at a time or something like that, I can get to this function, and we'll just hypothetically pretend that the function I have the arrow over is the function that would be doing VM detection. It would look all over what programs are running in Windows to see if any of them look like they're drivers for a particular virtual machine. It'll look, there's actually some CPU tests that you can run to try and see if the CPU is in virtualized mode. There are actually ways to trick that at the VM or at the hypervisor level as well. There's also some other tests that you can do looking at certain data structures in memory and stuff like that, and also looking at like the system BIOS and everything. You can try and see if VMware or VirtualBox are present in the system BIOS, for instance. Yeah. But of course, naturally, if I want to make a hardened VM, I can change all those things, right?
You can comment it out.
Yeah. But in this case, what I could do is exactly, I could basically this test that's happening here with AL, I could actually flip this logic to basically jump if 0 instead of jump if non-zero. So I can flip that logic. Or if I really want to, I can just comment out all 3 lines of code here with just a no operation. So I basically turn them into code that has no effect at all. And then it would just immediately go down here. And so a lot of times when I'm analyzing malware and I identify it's doing that, instead of trying to figure out all the hard ways I can to try and confuse it into believing it's running on real hardware, I'll just go through and then overwrite a few bytes in there with basically a non-operation or something like that. So the other thing that's nice is that you get access to all the memory, which is something you definitely don't have access to. So in addition to all the memory that a program has to put its code into. So remember when we looked at the file on disk, the exe file was broken up into many different sections, right? So those sections are typically loaded into memory, and there's a certain structure that's replicated by Windows. So Windows creates a bunch of different sections in memory and then loads those sections off of disk and puts them in memory. But while the program's running, it can also allocate new ranges of memory for its own use at runtime. So to pull in that example of obfuscated code or compressed code, it's very common for a program to load up and have a small amount of code that just decrypts a part of itself. But the part of itself that's encrypted may not ever, what's the best way to say this? The area of the program that's encrypted may end up needing to have a basically separate empty array of memory allocated for it first. And then what happens is it runs it through the decryption routine and slowly fills up this brand new section of memory. So it's a section of memory that's actually not reflected in the file on disk. Right. It's only known about at runtime. And then after the program exits, it gets wiped out, disappears.
That memory will be allocated dynamically.
Yeah. So it's basically a dynamically allocated section. And there's a function called virtual alloc is a common one that's used that actually allocates those memory ranges. So putting it through a debugger and analyzing this execution environment, you can also identify the point in code when that memory allocation happens. And you can actually write heuristics that look for if you can actually script a lot of this. So I can script something that will step each one of these instructions one by one, and then after it executes them, then it runs a certain series of checks against the program to see if it's changed any, like if its memory space has a new section present or something like that. And if that occurs, then I could dump the contents of that into an artifact file or something. So that's, again, what's helpful about the execution environment. The program stack is another section of dynamically allocated memory that is typically reserved for arguments and return values, and also
Local memory.
yeah, local memory, typically local small memory storage. So one of the benefits of the stack is that if you've ever run a program that crashed, a lot of times you'll get what's called the call stack, which will be this series of functions that led all the way back to the main function to get you to the current place where the program crashed. All of that information exists on the stack. None of that information exists in the file on disk. So you can only get that information typically by either simulating execution, which is one possibility, or running it, in fact running it, and then dumping the execution out. And you can actually see some of those addresses are actually listed up here. So for instance, this one right here that's highlighted mentions something about a return to that function inside of the kernel 32 library. And then there's another one down here that's near the arrow. And then finally, there's wmplayer.module entry point. So those three things might be the sequence of steps. I'm not entirely certain where this is I didn't analyze this file, so I don't know. I don't have a frame of reference to a lot of this stuff. But those series of steps might be the call stack for this particular program. So, and then finally the registers and the flags. So this right here, if you'll recall when we talked about how the processor is built, in very rough state. I think it was during that first assembly language lecture. The processor has some local memory. So I have the registers right here, and there's 8 of them. So in a 64-bit system, there'd be 16 of them here. And they'd all start with R instead of E. But basically, that's another thing where you have entire visibility to this. And so, at its core, when the program is executing instruction after instruction after instruction, it changes these things around based upon each instruction. So you get complete visibility into all of those things. So all the registers you can directly access. These over here. You also get direct access to the current instruction pointer as well. So the register, I would say the hidden register that's inside of x86, because in x86 you don't actually get to ask it what is my current execution location. That's only something that is basically inferred. The debugger actually lets you see that through, and there's a number of different techniques that they can use for doing that. It lets you see the different segment registers, which I'm not going to get into too much, but other than just to say that they're traditionally used for setting up memory mapping. The other thing you get is the flags. So this will be really helpful to read about, and I didn't get into them too much in the assembly language class because I think that they'll just make a lot more sense in context here when we actually get to debugging code and everything like that. But for all of these, this is JNZ. For those of you who can't read the in the room here, it's very difficult to see the instructions right here. So this one where the arrow is JNZ, which is conditional jump. That means jump if not 0. This one where the arrow is now is called JE, which is jump if equal. And then there's another one down here that's JL for jump if lower. or jump if less. So those things are actually testing these flags right here. So there's 9 flags right here. So based upon and the flags themselves are Boolean values, so they're single bit values. Based upon the value of any one of these, or maybe multiple of these, the condition evaluates to either true or false. And there are conditional jumps for every single one of these flags, and then there's also a handful of conditional jumps that use a combination of the flags in order to influence their decision making. So, and that's another thing that we'll get into later on when we're actually doing the program flow debugging and everything. But in a nutshell, that's the type of information that's available from analyzing the execution environment. And just like I was saying that, I carve it up into these things mainly because I can pinpoint specific tools that are effective on analyzing each one of these things. There's a lot of file system analyzers out there. There's a lot of file system forensic analyzers. The debuggers that you use, a lot of those are execution environment tools. And so here's the execution environment impact example, I'd say. And you'll notice that there isn't as much noise, so there aren't as many parentheticals on this one as there were on the system execution thing. So, and this isn't hard and fast either. This isn't necessarily supposed to infer any sort of limitations that exist in the debuggers or runtime analysis if you want to do it. But just hypothetically, the idea here is that the debugging and the execution environment analysis is useful for identifying when bad guy code, when the attacker code is actually running on the system. So in this case, user downloads bad, will basically replay the attack all the way down to step 3 where bad PDF exploits Acrobat Reader. So really what that means in a nutshell is that the PDF that was given to the user by the attacker is able to perform what's called arbitrary code execution or remote code execution. And actually memory writes as well. So in addition to it executing some random code, it's also writing some data that's pertinent to that exploit. That's probably is these 2 files. So these 2 files have to come from somewhere inside of the original PDF. It might be hidden in there in some fashion, but in order for these 2 files to be written to disk, they need to show up in the memory writes from Acrobat Reader at some point, which can kind of give you some insight into if I wanted to have a tool that's analyzing Acrobat Reader instances in my environment for attacks, I might actually have it go through and do memory analysis to look for certain characteristics that I've learned from analyzing this, statically analyzing these 2 files. So then, that shell code basically executes both of these things, so it performs a number of actions. I specifically highlighted this 5th action as something that might be very out of the ordinary for Acrobat Reader to do. So in this case, the shell code that's running isn't running in a program of its own. The shell code that came from the PDF is actually running as if it were Acrobat Reader. So all the actions that the attacker had the exploit do is actually being executed by Acrobat Reader. So Acrobat Reader itself, out of the package, has a specific defined set of behaviors, and then those are further limited to what, say, people working at your company might, in a more limited sense, use Acrobat Reader for. So in this case, if we happen to see Acrobat Reader opening using Windows API calls, and I call WinAPI here, you can actually search for that on the internet to get the documentation about all the different functions that exist in Windows. But here, if we see
the system call,
mm-hmm.
but, you can call it exe inside of
yeah. Yeah, so it's kind of like a system call. Yeah, so if you're familiar with the Unix system function, right? It's kind of like this. Microsoft Windows has a core API call that's called create process that basically creates a new process for execution and can do it by opening an existing file. Or there's a handful of others as well, like shell execute and stuff like that. So it may call one of those many functions. That behavior itself might be out of the ordinary for Acrobat Reader to do, and itself might be something worth looking for. So finally, bad.exe. So then this other program that's running now ends up causing a bunch of other stuff to happen. And I'd say that a program deleting a file isn't abnormal. A program writing a symlink itself isn't abnormal, although a program writing a symlink into the startup folder might be something worth looking out for. And then finally, a program opening a network connection itself isn't necessarily out of the ordinary either. And that's why, even though these are actor code, these are adversary code, I'm not necessarily highlighting them in this because they're not necessarily things that by themselves would be out of the ordinary to see occur. So the next thing that we'll talk about is operating system and user configurations. So most normal working systems are desired to operate under a decently high level of security. So a lot of you will remember that when we first set up those malware labs, we had to turn off some of the security features that existed in Windows, and I kind of had a checklist of a number of those. So in this case, it's not uncommon for, say, if the following sequence of steps happens, it's not uncommon for the adversary to actually make some of those same changes that we made earlier on, which is another good reason why it was an informative exercise for us. So some examples of configuration changes might involve these things. So adversary might change the default proxy settings. So for instance, if your company kind of selects for a lot of their users to go and use a proxy that's supposed to only give them safe websites or only give them company authorized websites, they could hypothetically try and change those settings to try and bypass the proxy and go directly out to the internet if they wanted to. There's user authentication check, so this kind of gets back to what you were saying earlier about the malware trying to get administrator level access. So a lot of you are familiar with, if I install a program in Windows or install a new driver in Windows or something like that, it usually pops up a window that says, hey, this program wants to install a new service or install a new driver or do some administrator task. Is this okay? Yes, no. So that's called user authentication check. And there's actually ways, there's a number of ways for some malware to maybe easily click yes for you sometimes. So event logging. So if you are logging a lot of events, so if you're keeping track of what's happening on your user systems, that might actually be useful for you as a kind of forensic analyst to try and go through and see or help you understand what happened on a compromised system. In order to try and conceal, cover up tracks, you can actually, an adversary can actually go in and change the event logs to try and turn down the settings so that there's less breadcrumbs left behind. And then service changes, so turning some services on or off, which is kind of what we did when we turned off like the Windows Defender and the firewall and things like that. They may also want to turn things on. For instance, if they want to overwrite, they may go, I would say, a common approach I've seen, and I'll go over here to kind of demonstrate it, right? Did that? Oh, that VM shut down. Oh, that's fine. I'll just start it back up. Excuse me. So I'll boot Windows back up for a second just to kind of demonstrate this. But the idea is that there's usually a lot of services that are running in Windows This thing's mainly mad just because I haven't, what you call it? I haven't activated my malware VM copy of Windows. So it shuts down after an hour of use or something. So while that's coming up, I'll say that a common approach that I've seen has been that Windows usually has like maybe 100 services. It can be some turned on, some turned off. So something that's very common for malware to do and might be very useful reason for taking inventory. So I'm going to just click OK to all this. It's important to use activated version of Windows. So if I run the services control panel thing, right? You can see that there are lots and lots and lots of services, but only like this one is started and this one started, right? If I was to jump into one of these and maybe go to properties, I can actually see that it lists a path to the executable. So this is actually something that's inside the Windows registry, right? There's a description up here. There's a startup type. I can start and stop it. I can tell what account is going to use it. I can even tell other services to be like dependencies of this and stuff like that. So one thing I've seen malware do is they'll go in here, they'll look for something that's already turned off, so something that's been disabled. They will overwrite the malware's startup info over this, which I can't edit this from the dialog box, but I can change it in the registry. They'll overwrite that with how to run the malware, and then they'll turn the service to be enabled. So that then, when I'm a user and I'm looking through this, trying to figure out how the malware is installed, like I can't find it on here. Because number one, the file that's run, the file path that's run is not listed in here. Number two, for some of these, it's actually not uncommon to have an environment where in the office, some of them are running on some people's computers, and then on other people's computers, some of them are turned off. So a lot of times what you can do, and this is where being able to have a tool that can inventory these things, or if you have a forensics lab or something like that, being able to have a record of what the original path to executable would have been, then when you're running through investigating a system that seems to have been misbehaving or whatever, you can actually compare what it should be with what it actually is in the system and figure out what service they hijacked, and then that might be informative to you to understand one of their kind of tactics. So that's another very common piece of service changes. So that when I'm talking about service changes, that's what I'm referring to. So Windows contains that persistent configuration database known as the System Registry. So I'll minimize this again just so that I can do this. So I can actually run.
Well, how would you know that the registry is being,
modified?
Yeah.
Oh, okay. Yeah. So, well, just to kind of look in here. So here's the system. Here's the system registry, and it's basically this big hierarchy, right? One of the things that happens is that you have to just go to this. Is that in order to interact with the Windows registry, you actually have to call a number of registry functions, and so this is one of them. There's actually a bunch of them. So see, they have some of the others down here as well. So the registry has what's called keys, which are basically directories, and then it has things that are called values, which are actually files. And so values are actually key value pairs inside the registry. But basically, you can look for these functions being called because these functions are only called by things that are trying to change values in the Windows registry.
I mean, if you do any static analysis,
Yep.
how would you know that registry is being?
Well, yeah, so for static analysis, you may not know right off the bat. However, if I was to use that obj dump tool, so we'll go and look at that, right? So I can't remember if this thing, no, I don't have it in here. But I think I do have. And I don't have it in here. Can't remember. If I can't find it very quickly, let me see. I don't know if I have it in here. There we go. So we'll look at that one, right? So this is one way that maybe I could glean that it's that this particular program, because this is the third program I tried to find it in, right? So I have a reasonable level of certainty that this particular program is trying to modify the Windows registry, whereas the other two programs I was looking at, they don't have any code, at least obvious, in them. It's very possible that there's some obfuscated code in there that is only available to me if I'm doing runtime analysis that does it. But in this case, at least this is the one that actually has it embedded in the static notes, the static metadata of the file. So what this is saying here is that this program is telling Windows, so it's written into the program import section, it's telling Windows that in order for this program to run, this program needs to have the ADV API 32.dll loaded, so it needs to have that available and loaded, and then it needs to be given the address to these three functions from that DLL. So it'll support many different versions of that DLL, but whatever version it has needs to have all three of these functions in it. And when Windows loads this program up, it also loads up ADV API 32.dll, and then it goes into that DLL and it looks for those three functions, and then it makes sure that it updates in memory the address to name linkages. And that's actually what this is right here. So, or I should say what this stuff is. I guess I can't select the entire line. So it basically tells it where to put the address of those things. That's what this index is. So that's one way that you would use to find out, hey, does this thing, is it obvious whether or not this program modifies the registry? So in this case, yeah, in this case, and whoops, I have a couple errors here on these two. But the big one here that I was kind of pointing out is that one of the configuration things that are in Windows is the user profile. So the user can actually change some of the default folders and stuff like that. You can change what your temporary folder is. You can change what your downloads folder is and stuff like that if you want to. So you can actually change where the default place is that Internet Explorer is going to download files. Or you can change where the default place is that if you're running a Microsoft Office program, that it's going to write temporary files to disk and stuff like that. So in this case, the attacker shellcode might actually use, instead of having a hard-coded value, it might actually use the environment variable that's configured for that user in trying to decide where to write a temporary file. That means that it's a little bit less obvious and a little bit less easy for you to write detection that works across many different systems. If you have, say, users who may have their temp folder somewhere in the D drive, and other users that have their temp folder somewhere in the C drive, or some users that might actually have one that's network mounted or something like that. So Again, a lot of like the service changes and stuff like that we talked about in this particular attack example. Those aren't actually listed up here. So persistence mechanisms. So I got into these earlier. A subset of configuration is called persistence mechanisms. So I liken kind of this to almost a very case or use case specific version of this. So it's a handful of these operating system and user configurations actually are persistence mechanisms. One of them actually is, and it's this one right here, and it's the one that's used by this attack, is actually a file system change. So just some background, because earlier versions of Microsoft Windows used to allow users to basically drag and drop application shortcuts into a startup folder as a means for telling the computer that I want this program to always start up when I turn it on or when I log in. Current versions of Windows preserve that feature. However, other versions of Windows that were like earlier versions of Windows NT and stuff like that that were more kind of enterprise focused actually had that type of functionality built in as a registry configuration, rather than using that kind of startup folder concept. So that it could be done, so that it could be something that's done as a system-wide or a network-wide policy. And current versions of Windows actually employ both approaches. The end goal here, though, is that persistence mechanisms are very common because they allow the attacker to maintain presence on the machine that persists against reboots. So I can sleep my computer, take it home, start it back up, program will come back up. Normally that's the case in most of your applications. But if I wanted to, I could reboot my computer. Like if, especially nowadays, that's extremely important because you probably reboot your Windows system like every 2 weeks or something like that because of just the high rate of patching that goes on nowadays. And the fact that like Microsoft forces you to install those sometimes. Registry entries can be inserted that instruct a certain program to execute on startup. Hijacking or creating a service that encapsulates malware. So that was kind of the version of it that I was showing earlier, was identifying a service where you kind of plug your malware into it. Another one that's not always obvious is, but I've seen it, is replacing or hijacking common runtime libraries to load malware. So for instance, just to go back to the example that I had here, and this is why kind of explaining, come on, I'll do this so that it's a little bit more obvious, or so it's easier to reach. So for this ADV API 32.dll that it needs, if I was to make a copy of that DLL somewhere else, and then I was to overwrite that DLL with code that exposed all the functions, so that replicated all the functions, but then executed some random code of my own, and then also called, as a last step, called the, or jumped to the function that's inside of my copied version of the library, that interaction would be pretty transparent to the application that originally asked to install ADV, or asked to use ADV API. So it doesn't care what version of ADV API, and that's where that wisdom comes into play, is that it doesn't care if it's the Microsoft or authorized version of it or something else. All it cares about is there a library that in this case has those 3 functions in it? Now, just like any other library, that library can then call other libraries, right? So that library can run bad code and then call the real version of it. And then as long as the return values are lining up and the data structures created in memory are looking correct, the application doesn't really care, doesn't really know what's going on. And that's another common persistence mechanism because like a lot of these Windows system libraries are used by almost every single application. And since you never start your computer up just to stare at the desktop, you usually start your computer up to run a program, right? So as long as you can find a library or two that are used by most of the programs in the system, eventually that malware is going to get turned on. The other nice feature about this is if someone ever takes the computer that's powered off and they try and start it up in a lab and then just leave it running idly, it's not going to do anything unless you actually are poking and, unless you're actually using it like a user. So it makes it a lot, it's a popular technique, but again, it's one that if you end up having kind of an inventorying system set up where you're taking inventory of all the libraries and stuff like that on your computer, then you can thwart the attack by identifying when some rogue version of a library gets put on there without going through like the normal patching process. Scheduled tasks is another one that's also very popular, and that one is many of you who are familiar with like Linux systems probably are familiar with the concept of cron jobs, right? So this is the Windows equivalent of those.
Yeah, Windows.
Task scheduler, right? Yeah. So I don't know if I can. Only have a little bit of time left, but task. Let's see. Schedule tasks. Yeah, or task scheduler was up there. So I don't know what version of it this is going to pop up. Yeah, so task scheduler, right? So I don't even know if I have any on the system. I probably don't, but yeah, here we go. So here's some, right? My favorite thing is trigger, right? Add startup, right?
Yeah.
So I can actually add new triggers in here. I don't know how to use this tool. Yeah, there it goes. It's just slow because it's in a VM. So on schedule, at login, on startup, on idle, on a specific event. So there's all these things that can call where you can plug something in here that'll run some arbitrary command on your computer based upon some arbitrary event. Like my favorite is maybe like this one, right? On workstation lock or on workstation unlock, right? So, there's this one might be neat because it's like really broad. So this allows you to have a program run in response to a system log action occurring. So any one of the possible system events that Microsoft Windows knows how to log can trigger your program to run. And so that's another approach for getting malware to start, to start on install. Like a great example would be to have it run if cmd.exe is run or something like that. Because if a lot of you are familiar with like corporate environments, it's not uncommon to have, after you log in, a batch file runs, right? And that would be something that would be kind of very, might be a little bit confusing to analyze from like the defender perspective. So
it's going to schedule a task to copy your file.
Yep.
While you are sleeping.
Exactly, yeah. So you can even have a scheduled task to do specific things. So for instance, I highlighted one here that does it, and that's just like the startup folder and start menu. So the reason why this action was taken, the purpose of this, the after effect of it that's desired, is that bad.exe will start the next time the user logs in, or I should just say every time the user logs in. And then finally, network traffic. And I'm not going to dive into this one too much, so I don't, yeah. And actually, I'm not going to jump into this one at all. We'll pick up network traffic later on because